In this unit, we're going to see two major themes. One is the idea of level curves, and they are going to be an alternative to the challenges we had graphing in the last unit. And then we're actually going to get into the calculus ideas of derivatives as applied to multivariate functions, or functions of two or more variables. And with no further ado, let's jump right into that. We're starting off with the contour diagram or level curves of a function as an alternative way to represent or graph a function of two variables. We'll start there. I recommend looking at the textbook in this particular section simply because it has a lot of diagrams and a lot of the skills that you'll learn in this section are facilitated by having seen a whole bunch of different graphs and how they relate back to the formulas for f of x, y. So I highly recommend at least browsing through the pictures in section 12.3. All right, let's make this as concrete as possible. We've got a function h of x, y, which gives literally the height, so a z value in the third dimension above that point on a surface. What we actually are talking about there is an actual landscape then. At a certain x and y point, we have a certain height. Now if we do that, we would get a surface. That would be the graph of h of x, y. But as we said yesterday in the last unit, this kind of surface would be obviously very hard to draw by hand. So what kind of alternatives do we have? Well, one thing that we can do is build a contour diagram that's an alternative representation. And what we do is we look for the level curves, or the sets of xy points, all at the same level. And when we say level, we mean z value here. So if we trace through, say, this circle here, as we go up to this peak, there are a set of points that are all at the same height around that peak. And what we do is just map that down onto the xy plane and say, oh, well, all these xy points are at the same height. Likewise, a set of points around in a circle here are all at the same xy level, or same z level. Well, what that lets us do is take something that was three-dimensional and bring it down and represent it in 2 dimensions. Here's what that diagram would look like in just the contour diagram. And the way to imagine this is that you're looking down from above. And what you're seeing is all the points at height 2. Well, there's a whole bunch of points at height 2 on this contour. There's some more somewhere else, but this contour in particular is height 2, then it's height 4, then it's height 6, and then height 8. So this is coming up towards you out of the page. Contrast that with going this direction. Here we have contours at height -2, -4, -6. This is going away from you or into the page. Whereas this way is going upwards or out of the page. And the way we know that is the z values, which are the labels on the contours, are increasing as we move outside in. And again, any of these directions here lead us towards the peak. If we look at this part here, so this is the opposite situation. We have z values that are decreasing in scale, -2 to -4 to -6, getting more and more negative, going downwards. And so that indicates that we're moving downwards in the surface, and there's actually a valley at the bottom here. So looking at this entire diagram, we see that there's a peak located in here. There's another contour at height 2 here compared to 0, so it would be going upwards to here. There would be another peak here. And we saw it just on the edge of the diagram before. Looks like there's another little side peak over here. Meanwhile, going down this way, we have a valley, or a pit, it's sometimes called, and another one over here. That would be another valley, 0 down to -1, and inside there somewhere is going to be a minimum of the surface, or a little bottom well in the surface. we can apply this idea to real contour diagrams, what many people might be familiar with, topographic maps, where you show something about the surface that you're dealing with, not just the roads, but how the land is shaped using contour diagrams. So typically, these lines represent evenly spaced heights. So without these being labeled, so if we assume that they're evenly spaced in Z, the third dimension, are coming in or out of the page, it's pretty clear that we have a hilltop, thus the label Signal Hill, and we also have the city down here at the bottom. And what we'd imagine is, well, we could walk up from the town to the top of the Signal Hill, and what we would see is, as we're going northwards in this diagram, we would be crossing contour lines and going up and up and up and up and up and up and up towards the peak. Now, one little note about that, if you've had some experience with contour diagrams, especially for hiking, you'll recognize that there's two very different routes that you would experience. One if you went this way, and one if you went this way. Let you think about what that would feel like if you're on the surface, or what that would look like if you're walking there. I think you see, I hope you see, if you've worked these diagrams before, that if you went up this side, you'd be crossing contours very quickly. For each step that you took in terms of the map direction, you would be crossing here 1, 2, 3, 4 contours. Whereas that same distance here only takes you up 1 contour. Well, what does that tell you? It means for a certain step in X and Y, same step in X and Y, here you're going up very quickly. You're crossing many contours. And here's the important thing, per unit step in X and Y for that XY step. And that means it's a very steep surface, or path over that surface. We'll say it's steep surface there. Actually, no, let's say path on the surface. Meanwhile, if you went this way, this particular shape here, or this path here, would be a less steep path up the surface. All right, so that's something we're going to bring into bear as we go through looking at different kinds of contour diagrams. Just to summarize all that, in principle we can map between these two ideas, the idea of the surface being a two-dimensional bent shape living in 3 dimensions, and its corresponding contour diagram that only lives in 2 dimensions. The contour diagram is just drawn in X and Y. Here we draw them together just to see the relationship. And what we get is a simpler but less detailed idea of what the surface looks like. From this contour diagram and the labels on the contours, we need that information as well, we can see, okay, we're at height 15 around here, then 14, then 13, 12, down to 9. That tells us, just by looking at the contour diagram, that we have a swell in the surface and then it goes back down again. So that's very helpful. It doesn't tell us quite as much as the surface itself. Like the surface here, we can tell very clearly by looking at it, there's a single peak. But the contour diagram wouldn't say that uniquely. Maybe there could be multiple peaks in the middle here if we had other contours. So we are trading something off by using contour diagrams instead of surfaces, but for the mathematical kinds of functions that we typically work with, that simplicity is just fine for what we need. In terms of the formulation, how do we obtain these contours? We take the function that's given and we set it equal to a constant. And then we solve for the x and y curve, xy relationship that comes out of that. And we try to graph that if we can. And we're going to get some practice with that as we look at the following examples.